welcome everyone. We usually have a really great lecture series that's in person, but we're going online because of Corona, as you all know. And that's actually a good thing, because we can bring in great speakers like Masoud. I just want to do a very quick intro. Masoud Akbarzadeh is a designer with a unique background in architectural design, computation, and structural engineering. He's a professor of architecture and structures and advanced technologies, and the director of the Polyhedral Structures Laboratory, which is called PSL, at the University of Pennsylvania. He holds a doctorate in science from the Institute of Technology and Architecture at ETH Zurich. He also holds 2 degrees from MIT, a Master of Science in Architecture Studies and a Master of Architecture, actually, and his thesis earned him the renowned SOM Prize. He also has a degree in earthquake engineering and dynamics of structures from Iran University of Science and Technology, and a BS in civil and environmental engineering. His main research topic is 3-dimensional graphical statics, which is an innovative geometric method of structural design in 3 dimensions. In 2020, this year, he received the National Science Foundation Career Award to extend the methods of 3D polyhedral graphic statics for education, design, and optimization of high-performance structures. So without further ado, I just wanted to introduce Masoud, and thanks so much for staying up late with us and lecturing from the University of Pennsylvania.
Absolutely. Thank you very much, John, for the great introduction, and really appreciate the invite. It is a great honor for me to present some of the work that we are doing at the University of Producing at the University of Pennsylvania. So the name of the lecture is called Spatial Efficiency. And before I start, I would like to give you a little bit of roadmap. That's what this talk is going to be about. So first, I just provide a brief introduction about the mission statement, what the lab is, and what is the approach that we have at the lab, and then provide you a brief history, where does the core methods of the lab coming from, and then introduce you to the methods of 3D graphic aesthetics, which is the core subject of the design research in my lab. And then review some of the design methodologies and tools that we've been working on in the lab, and the application of those tools as design manifestations. And then at the end, I would conclude by getting back to the natural structures and see what we can learn from nature. So I established Polyhedral Structures Lab in 2017, January 2017, and basically, it is a small group of associate researchers, postdocs, graduate students, and basically PhD students. And the way that we work in the lab is that obviously the geometry-based structural design methods, which is called 3D graphic aesthetics, and the entire talk is going to be about, is at the core of the methods of the lab. So we conduct theoretical research, because this methodology of design and engineering is actually quite new. So we conduct theoretical research to expand the applicability, or basically understand some of the unknown corners of this new science. And then in the meantime, we also apply that research in the construction projects and material methods. So as a result, the primary domain of research is basically architectural design and structural engineering, but the work can extend to mechanical engineering, computer science, mathematics, material science, and so on. For the purpose of this research, this presentation, I'm only going to present the work that is related to construction research and material methods, because I assume that many of the audience are from the architectural school and designers. So I won't get into the technical research methods, and I would not get into the other fields. And I hope if you're interested, we can actually talk more, or you can basically follow us on our website or the papers that we publish. Now, before I start showing you some of the work we're doing, then I have to provide you with a little bit of background about the formation of this research, where it is coming from. And I would mention quite a number of people who actually played an important role in shaping my career as of today, right? So I'll start with the very famous example. Well, almost all of you know Antoni Gaudi, and many of you might know him as an architect, structural designer maybe, or artist and sculptor, etc. But for me, he is a little bit more than all these, because he had a unique understanding of the limitations of the material, the construction materials that he was working with. And he knew that in order to create architectural spaces, he had to make sure or assure the stability of the systems. And he was creatively combining Art Nouveau artistic detailing with the engineering aspects of stability and basically performance of the structure. So if you don't know about his methods of design, he was actually using ropes and sandbags to basically find the structural form of his designs prior to architectural detailing. And this was quite unique. And this, I believe, the method that he was using for design made him quite famous and made him basically quite important among his contemporaries. So this method of design, which is often referred to hanging chain, was proposed originally by Robert Hooke in 1676. So if you don't know, if you basically take a piece of chain and if you hang it from based on its own self-weight, it would create a form that many people that are in the field of architecture and structural design would call this a funicular form. This form is actually in pure tension. And interestingly, if you reverse this form, it would be a perfect form in compression under the self-weight. Obviously, if buckling is not an issue, and if you're, for instance, dealing with stone as a construction material. So it's a perfect method to find efficient structural forms for masonry buildings. So in fact, Audi was designing everything upside down, and this was quite unorthodox, because he had to develop these models and make sure that he understands the force flow of the structures he's designing, and then using other means and mediums like maybe mirror, he was using this reflected image and then drawing on top of this reflected image to articulate the architectural details of the space. And everyone agrees that his designs and his works were, are, and will be groundbreaking and extraordinary. So the question is that, yes, basically funicular forms are efficient forms that we can use in design, but how can we find them, or how we can actually understand their geometry? Obviously, yes, you can start by partial differential equations and do maybe 5 pages of calculations to finally get this funicular form that is basically connecting to points with particular length of the cable. But there are simpler methods to find that. In fact, in 1725, a French mathematician, Wagenion, was interested in finding those funicular forms and the equilibrium of forces in them using geometric constructions. So simply put, if you have a rope that has been pulled from 3 corners, you can just simply put lines perpendicular to each part of the rope. And if the lines would actually create a closed polygon, your system is in equilibrium. And more importantly, the magnitude of the force in each rope is equivalent to the edge length of that polygon. This is fantastic, because now if you have a funicular form, you can do the same for each node, and basically combining them together would give you a secondary diagram that describes the equilibrium of forces in the system based on pure geometry. So this method was the basis of the method that is called graphical aesthetics, and it was for the first time put together by Carl Kuhlmann at ETH Zurich in 1866. In fact, in graphic aesthetics, there are 2 diagrams, geometric entities. One basically represents the geometry of your funicular form, including geometric properties, edge length, applied loads, and the location of supports, etc. And there is another diagram, which is a force diagram, And that represents the equilibrium of forces. And these two diagrams are basically related to each other because each polygon in your force diagram, the closeness of it will tell you that there is a node in your follicular form that is in equilibrium. And the edge length of that polygon would tell you the magnitude of the force in that member. More importantly, these two diagrams are geometrically dependent. That means that if you change one, you can immediately see and observe the change in the other ones. So it's a very powerful technique. But when was the first time that I was actually introduced to this technique? It was at the class at MIT. I had a chance to be a student of John Oxendorf. And John basically, the other John Honk, who introduced me, mentioned that I have an engineering background. Yes, I do have an engineering background, but I've never actually, I never heard of this technique in the engineering school. And funny enough, I heard a lot about the way that John is actually teaching a structures course in the architectural school. And for the first time, he introduced the methods of graphical aesthetics by showing the works of Rafael Guestadino. So Rafael Guestadino was a famous Catalan wall builder who migrated to the United States the beginning of 20th century. And he was very famous for the thin shells he was creating with the tile wadding, very thin tiles that could take up to 500 times of its own weight. So you could immediately see the efficiency of the system that he was using for his structures and buildings. And funny enough, he was using graphic aesthetics to find those forms. You can clearly see the thickness of the section he developed using graphic aesthetics and the diagrams of the form and force geometrically that he was using for those basically geometry. So that was the beginning of my introduction to the methods of graphic aesthetics. And later on, I realized that yes, even Gaudi was using graphical methods. If you haven't had a chance to basically visit Park Güell in Barcelona, this beautiful structure has been designed using graphical methods, as you see on the right. So it is impossible through the history of construction, especially the stone construction, that you visit that history and you do not find the traces of graphic aesthetics being used or applied in the design and construction of these buildings. If you move a little bit further through our contemporary basically practice of engineering, probably many of you have heard the name of Pier Luigi Nervi. So he was an Italian structural designer, and he was quite famous for the efficiency of the structures that he was designing and building. And you can see, well, you don't see because you don't see the drawings here, but he was using also the graphical methods. And there are many examples like Robert Maillard. If you've probably seen this, or you haven't, you have to see it. And if you had a chance, you should definitely visit this bridge in Switzerland and many other bridges that he designed. He was also using graphical methods. To more contemporary engineers like William F. Baker, it was also brought into my attention that Bill has a research group, and in his research group, they are applying these techniques even today in the design of efficient structures. So for instance, in this case, they are using graphical methods to optimize the use of material. And the form is actually extracted from the force diagram on the optimization of the force diagram. But clearly what you see here is a great potential, but in the meantime, there's a bit of limitation because this method for the past 150 years has been a two-dimensional method. So in 2009, Philip Bloch, who was a student of John Oxendorf, developed a method by combining two-dimensional graphic aesthetics and numerical approach to design three-dimensional compression-only free-form shell structures. So at the time, this was a groundbreaking, it still is a groundbreaking contribution because now you can basically design efficient structural forms. For instance, in this example that beautifully demonstrates the power of this technique, you can basically make sure that the entire construction material is actually following the force flow. For instance, in this case, 399 blocks of stone held together with no mortar and by compression only force, right? If you're interested, you should definitely check out this book, Shell Structure for Architecture. I also had a chance to have Philip as my teaching assistant when I was actually a student of John Oxendorf. So I knew him from back then. And I also had an opportunity to join his research group in 2012 as a PhD student. Now, by the time that I joined his group in 2012, when I was going to start my PhD, the question was very well clear, right? So if in 2 dimensions, the equilibrium of a single node can be represented by a closed polygon, and the edge length of this polygon can represent the magnitude of the force, what is the equivalent of this method in 3D? Very well. So I visited the literature, and I realized that this 3-dimensional relationship between form and force was actually proposed 150 years ago in a philosophical magazine by a professor called William John Macron Rankin. So you would be surprised to hear that, but this piece of text that you see on the left side of the screen, this is the entire publication. It's a half-a-page publication that he had it in a philosophical magazine. And this was actually the core of the methods of 3D graphic aesthetics. And he calls it the principles of equilibrium of polyhedral frames. No illustration, no proof, nothing. Just like one paragraph, boom, principle, you have to accept it. Well, funny enough, it took me 3 years to understand what he is actually trying to say in that very densely written paragraph. And then by the time that I was writing my PhD, I reached to the last paragraph where he's talking about the topological relationship between these 2 diagrams. And I understood that, well, I missed many things, and that ended up being another chapter in my PhD. But anyways, I'm not going to read this text for you because it's very it's very densely written. It's not going to be helpful. But if you had a chance to read it later, give it a try to see how complex it is. Anyways, the gist of this publication, this very short publication, is that if you have a node in 3 dimensions, the equilibrium of that node can be represented by a closed polyhedron of forces. So polygon versus polyhedron, where each face of this polyhedron is perpendicular to one of the edges or the members of that node. Now, if in the 2D, one edge or the length of the edge was representing, represents the magnitude of the force, in 3D, the area represents the equilibrium of the force. Yes, so this was actually the beginning of the methods of 3D graphic aesthetics and using reciprocal polyhedral diagrams, right? So having said that, just knowing that a single polyhedron of force can represent the equilibrium of a single node, this might be sufficient for us as designer to start playing around with this idea, right? Now, if you know that a single polyhedron can represent the node in equilibrium, you can aggregate multiple polyhedrons, right? Because each of them can represent a node in equilibrium, and then create a force distribution, that this force distribution can represent the equilibrium of a spatial flow of force or a spatial network of forces in 3D. So obviously the equilibrium of each node is represented by a closed polyhedron in that distribution, and the magnitude of the force is represented by the area. With a little bit of patience, design patience, right? You can aggregate various polyhedral cells to create or establish a force diagram, force distribution. You can basically extract non-conventional spatial or structural forms in equilibrium based on that. So if you realize it's a completely different way of designing. In this method, you do not start with a form as opposed to the conventional method that you start with a form, you analyze it, you optimize it, and you basically try to make it for your design. Here you start with a force distribution. You design the geometry of the force distribution. You understand the topological relationship between these 2 diagrams. And then you extract a structural form that you know for sure that it will be in equilibrium, if the boundary condition obviously is addressed. Now, I'm actually using this technique of design in my elective course with my students here at the Weitzman School of Design. And you see there is no limitation with typologies of the structural forms and these creative ideas that they might have. in transferring the loads from boundary conditions, you see that there is no limitation in this. Obviously, as I said, if you want to translate this into real structures, other consideration should come forward, but definitely as a way to explore variety of different design possibilities for architectural structures is quite fast, right? Now, obviously, you can't do everything by hand, and you can't do procedural drawings of graphic aesthetics. So for that reason, we developed this plugin for Rhino, which is called Polyframe. It is still in the beta format, but I'm very hopeful that with the grant that we received from National Science Foundation, we'll be able to push this to the next level. But this is basically showing how the students are playing with this tool. So you always start from a series of planar faces that are put together. You don't have to know that whether how many closed polyhedral cells you're making. Basically, the software basically finds all those closed polyhedral forces and extract this funicular structural forms for you, that then you can actually play with that, constrain it to geometric object, and manipulate it, push and pull. But then you always know that all these solutions that you're exploring are always in equilibrium, because the force diagram does not change and the distribution does not change. The only thing that you're playing with is the geometric properties of your funicular forms, right? So these are some of the complex examples that students came up with. And you see that there's no limitation clear, well, in exploring a variety of different spatial structural forms. Now, so I use this technique again, as I said, as a non-conventional way of designing in a design research studio for the students. And as you see, students starts with the force distribution, and they're basically exploring various architectural geometries as a result, because it's very difficult to begin with a form that would be in equilibrium. So they have to develop this understanding between the relationships, the topological relationships that these geometric objects have in order to come up with final structural solutions, right? So we did this as an exercise to redesign Philadelphia International Airport, Terminal E, and they used this technique to basically come up with the structural modules. And for the sake of simplicity, they actually tried to keep it simple, and this module can actually aggregate, but obviously they can make it asymmetric or any other configuration they want. But just clearly, they were actually exploring the idea that how these structural systems can be used for the development of future airport terminals. What are the spaces they can create? How you can inhibit this structure? So the architecture is actually the structure itself, right? So I'm actually going to go through some of these examples, and they had to make really larger scale models, structural models, obviously. So this was also a very good exercise for us, because now we could clearly see that you can create a lot of really complex systems that are efficient in terms of the force flow. Now the question is that we need to take this back to the lab and really investigate the material properties. So I'm just going to take a break from here and then move on to the research that we're basically conducting at the lab. So one of the most important topics that we began investigating was the relationship between material and this method of design. So we started very small. We started by designing a cylindrical structure that is bounded to the cylindrical concrete test developed by ACI, American Concrete Institute, and entertain this possibility to see how much we can reduce material from that simple cylinder. So we designed a structure that could fit within that boundary condition. And at the time, we were actually looking through the methods of construction or fabrication of this, because yes, you can find really efficient force flow or structural geometry in 3D, but then the materialization is actually quite challenging. How would you translate this into the language of materials? So we went through a bunch of techniques, and finally we came up with this method at the time that we can 3D print the formwork and assemble the formwork, and then take off the mold after basically casting. Obviously, we had some difficulties because we had to make this 3D printing molds quite thin in order to be able to remove it afterwards. But then the hydrostatic pressure of concrete and et cetera, it was a fun exercise. Anyways, so this was a 12 kilogram sample. The height is 60 centimeter, 2 feet. And we did the load testing for this sample by constraining the top and bottom, making sure that the top and bottom members are not going into tension and everything is going to be compression only. And I'm going to basically explore and just let you watch the load testing scenario, right? So on the left, you have the load based on kilonewton, and on the right, you have the displacement. So a 12 kilogram sample, well, okay, so we had a simple buckling, and we thought that, okay, we lost the structure, but because of the geometric indeterminacies of the system, it could actually take more loads to go a little bit higher. So yes, 250 kilonewton, or 24 ton, or the equivalent of maybe 7 SUVs on top of each other. But anyway, so this is quite exciting because a 12 kilogram sample can take a lot of force. But more importantly, after basically we visited our data, we realized that all the members at the same time reached to its failure point. In fact, the structure exploded. This shows clearly the efficiency of the system, that we basically loaded the system to the point that the stress level reached to its maximum level at the same time for the entire system, right? So, but clearly we are actually having a really good structural system to work with. More importantly, right? So 12 kilogram can take 12,000 pounds, which is the equivalent of 24 ton. But we know that because we have control over the geometry of the force, we can come up with various techniques to change the design, right? So these are multiple subdivision techniques that one of my research assistants came up with. And as a result, you could see that for the same boundary condition, right, you can have a variety of different, for instance, compression-only systems that are topologically different from each other. So in opposed to the methods like topology optimization that always leaves you with just one solution that you have to work with, here you have the boundary condition, and without changing the boundary condition, suddenly you have a variety of different designs that are all compression only, but they're topologically different. So you can control different features. Next, we moved on to a bigger example that is called Hedgercrete. So this is, at the time, was the first structure built using this technique, larger scale structure. So this structure, in terms of the performance, is actually quite unique because it's a branching system, and the top chord is entirely in tension, and the bottom chord is in compression. So since the top chord is actually made out of concrete, the weight of the top chord basically keeps the bottom parts or bottom members in equilibrium, right? So I'll walk you through a little bit of details related to the system or structure. So the bounding box for the structure is 9.30 meter by 10.80 meters. And the maximum span is 5.40. And the height in the middle of the span is around 2.36 centimeter. So this structure was developed as part of the workshop that I had in 2016, summer 2016 in Tehran. And the students used the earlier versions of the software that we have. It was quite sketchy at the time, but so they used and they developed multiple structural forms to be built. And then there's something quite unique about this graphical methods, and that's the control that you have as a designer over the forces in the boundary condition. So we can actually simplify the entire structure into these boundary forces. So the FR represents the resultant of all the loads that being applied to the structure. And then this structure is supported basically in 3 locations or 3 supports. And you have 3 horizontal forces that are being also applied to the system on the top, right? You can clearly see. So the force polyhedron on the right represents the equilibrium of this, because everything is closed. The areas represent the magnitude of the force of the reaction. So you can use this subdivision techniques to subdivide the internal space of your force polyhedron or global polyhedron, and then derive the topology of your structure. But then the question is that, okay, what am I going to do with those top forces that are for horizontal, right? So I need to provide them to keep the system in equilibrium. So you can explore this geometrically and see what would happen if you make those forces to become 0. So those forces basically correspond to these areas of the side rectangles, the green rectangles, as you see. And then making the area 0, it's as if that you're collapsing that rectangle into a line. So as a result, your form would actually will turn into the following form, that the top chord would go into tension and the rest would stay in compression. So because we wanted to build everything out of concrete and we knew that concrete cannot take any tension, right? We had to come up with a different detailing for the top. So we came up with this particular detailing that separates the nodes from the members and then connects them with the steel plates. But again, because we wanted to successfully or effectively transfer the tensile force in the top chord, we water jet the middle plate, and then we basically put the tensile members precisely in the location that the tension force should go, and embedded everything within the concrete. So this is the prototype of the tensile node and so it's connecting member, and this is the construction scene. So the entire budget for the project was very limited, right? So at the time it was around, I believe, yes, it was around $10,000 for the entire construction. And so we had a lot of limitation. First of all, we were using foam as a formwork, and we had to use this 3 times because the entire process of construction was really difficult and basically costly. So we ended up making the structure completely symmetrical, so we could actually use that formwork 3 times for the members. So this is the completed structure, and I would let you watch the little video related to the construction process.
Hello.
Hello, Masoud, your mic is
Yes.
muted.
Okay.
Yes, if you
Sorry
could
about that.
restart
Okay,
where
cool.
you were starting before,
Yes.
yes.
So the continuation of this project is basically the next project I'm going to talk about. And this was exhibited at the AIA Center in Philadelphia, the Philadelphia Center for Architecture in January 2019. But this time, we were interested in pushing this concept a little bit further in terms of the force flow and possibly combining it with different materials and also revisiting the connection of the members. Because in the previous project, we separated the nodes and the members from each other. And basically, this project was basically an opportunity for us to look at a smaller scale system that can be used as a furniture. But in the meantime, it would address all the challenges that you might actually have in construction of such efficient structures in larger scale. So the idea of the project is actually coming from Salto, and the name of the project is Saltator, means dancer. But Salto in wrestling means basically holding, bridging, rotating, and basically bringing it down to the ground. So in the previous studies, we all visited the equilibrium of a compression-only node as a convex polyhedral cell. But then in this study, we were more interested in exploring the possibilities of working with complex and self-intersecting polyhedral cells. So what does that mean? That means that if you have basically a polygonal face, you should be able, if you want to basically work with the system, you should be able to control the areas of the faces of the force diagram because those represent the magnitude of the force. So together with our collaborator in Leiden University, we developed a quadratic function. The function looks pretty big, but to control the areas of the faces. And as you see, you can actually play with these areas while keeping certain edge length constants. But more importantly, you can make these self-intersecting areas, as you see, so the regions, to cancel each other out in terms of the force. And this is quite important because if the magnitude of the force in a force diagram is represented by a convex polygon, right? The magnitude of the force in a self-intersecting polygon is represented by the sum of the signed areas, meaning that if your area is actually flipping as a result of self-intersection, then you have to subtract that amount from the actual amount of the force. So in other words, there is a case or there is a point that you can completely make this summation become zero. And this is super exciting because now you can make certain forces completely disappear from your equilibrium system. So if you, for instance, start with this global equilibrium of a force diagram, right, as you see, there are trapezoidal faces in this distribution. And using this technique, we can make these trapezoidal faces to become zero area members, right? And as a result, what you would have is this force distribution that can represent a equilibrium in the system, that you have top and bottom faces, the members are in tension and the entire body is in compression. And more importantly, we wanted to make this a structure that we could move from place to the other one place, so we could not have a fixed joint supports. So we had to come up with a technique that we tie the top and bottom together to be able to install and deinstall it in different places. So the resulting structure is actually the body of the structure has 3.8 centimeter span, and the width is 195 centimeter, so it's around 2 meters. So it's 3 by 2 meter and 1 meter height. And then on top of the structure, there is actually a very thin glass structure that I would actually talk about it. So this is the test run, and we had to develop certain particular detailing for spatial nodes because the construction detail was different. This is structure. We had spatial nodes, and as a result, if you know that if you want to assemble the spatial nodes, it would be very challenging because they would collide with each other. So we had to come up with some technique that that we could easily put the nodes in place and lock them in their particular location without being worried that this node might actually might collide with the other node and prevent from the actual assembly. So we made bespoke basically detailing and developed the formwork, and we basically make sure that these detailing would be held in place with our particular formwork to make sure that we are taking into account all the construction tolerances and shrinkage of concrete. We also did lots of FE analysis to make sure that basically the connection can take enough forces during the assembly, right? So this is the assembly process after, well, the body of the structure after assembly, right? You can clearly see the nodes are directly connected to each node. There is no member connecting one to the next separately. So it's a node-based construction. And yeah, these are some of the images of the final assembly. Okay. But now the problem of glass or this composite structure was a different problem, because we had a structure that spans 3 meters. Now we need to design a glass system that can self-support itself and sit on top of the structure. So if we wanted to design this glass as a monolithic piece, the thickness of the glass had to be around 2.5 centimeter or 1 inch. So if you calculate the weight of the glass, it would be around like 500 kilogram, right? So 1,000 pounds. So this doesn't really make sense for a piece of furniture, because then you need a crane to basically move your piece of glass and install it at home. So we looked at the nature at this time, and then we were inspired by the natural, the lily flower, right, in Amazon River, and we translated the same pattern using graphical aesthetics to design the structure of the glass, right? So these are the FE analysis showing that the structure can work really well in that. But then at that time we had some construction limitations because of the scale, because of the size of the glass, and also the amount of detailing that we could have in the process of constructing the glass. So at the end, we had to do some simplifications, which obviously informed by the construction limits. And then we divided the entire top piece into 3 pieces of glass that they form a 3-hinged arch at the top of the structure, right? So this is basically the section of the glass. So each piece was basically thermomold in the oven. And there was a glass artist who, Judy Miziomski, actually, who helped us with this piece. So we had to do lots of explorations together with Judy. So this is the resulting piece after coming out of the kiln. So, and this is me holding that piece. This is the original piece that we tested, and we were not completely happy with the quality of the glass, especially the bottom part. We had some artifacts, but the good thing was that we already knew the entire process for the fabrication. So these are the final pieces that we basically put together for the fabrication of the glass. So we had to come up also with a particular detailing for this. There is a company in Switzerland, Dausil, that supported this research, and they provided us with a particular substance that we could use to attach directly the steel connection to the glass. So we used transparent structural silicon, and so this would avoid cutting the glass and inducing any kind of local basically stress in the body of the glass. And this is some of the basically scenes of the construction of the project. Yeah, so this was an assembly test that we did at the school, and then you also reassembled the entire structure at the AIA Center in Philadelphia, and basically showed that you can actually use this as a method of construction. But definitely, this is another research that we're currently pursuing to see how we can scale up the members. Another research I wanted to show you with, this is an ongoing research, and it's an investigation and a collaboration between Weitzman School of Design, Villanova University, Technical University of Darmstadt, and the City University of New York. It's called Ultra Thin High Performance Glass Footbridge. And the idea comes from the fact that, okay, the glass is an important construction material and also quite appealing in the field of architecture. But usually in the construction of glass domes, the form finding comes first, and then the rationalization comes after the form finding, because usually the glass comes as flat pieces, and there are two separate basically processes. So I'm going to show you a simple example that how 3D graphic aesthetics can actually be used as a form finding and rationalization of fabrication at the same time. So this is a single node, and the polyhedral tetrahedron that you see is actually its force distribution. And these two diagrams are basically constrained to each other, fine. We are subdividing the basically the force diagram, and as a result, you expect that the topology of the form will change to correspond to that. So you see that from a single node, suddenly you can actually go to a shell, right? Which is compression only. You can control the magnitude of the forces by the force diagram and the height of your shell as a compression only. But in the meantime, because of this inherent planarity constraint that you have in polyhedral diagrams, all the faces that you have in your diagram is actually planar, right? So this inspired us to look at the possibility of building a structure based on this principle, because now we have a technique that can combine form finding and fabrication in one approach. So this was an earlier, basically, visualization of the project, and the project was aimed for Glasstec Düsseldorf, Germany, but because of the COVID and many complications that happened, we were not able to finish the project on time, and it was a very challenging project, and it's still an ongoing research. So we are hoping that by the time that the COVID would be over, we would be able to also build this structure. But I'm going to walk you through some of the steps that we've taken so far and show you some of the ongoing process in this research. Obviously, the form and force diagram has been generated using graphic aesthetics, the 3D graphic aesthetics. So we had a clear objective in designing such a structure. First of all, we were looking for an efficient structure with a minimum use of material. And we were looking for modular construction designed for reassembly again. And for this reason, we had to reinvent the structural detailing of glass connection. And more importantly, because glass is one of the most difficult materials to work with, if we could control the flow of forces and fabrication for glass, we could certainly extend the use of this method to other sheet-based materials, right? So we did some preliminary FE analysis, and the preliminary FE analysis showed that, yes, this is feasible. Now the question is that how? And how basically, this question of how is very well tied with the construction technique that we're using. So we are going to use basically a hollow glass unit structure. So the entire system is going to work like a masonry system, but you know that making hollow glass units out of 1 centimeter thin glass is going to be really tricky. So for that purpose, we are investigating the possibilities of fabricating these hollow glass units. And currently we are using VHP tape, which is a very cheap tape provided by 3M. And the 5-axis water jetting milling machine, so the water jet machine that can cut the geometry of the glass prototypes in precise angle, and applying these pieces and keeping the plates together in a form of a closed cell. So again, remember, the construction material is an annealed glass, or it's just a window glass. It's not a security glass. It's this is the weakest material you can actually find in terms of the glass construction. And the tape that we're using also, although it's been used for facade in multiple buildings, it's a very inexpensive material and very easy to apply, right? So we are currently conducting lots of load tests to understand the mechanical behavior of a single construction module. And this load test has been done at Villanova University. And you can see clearly from the movies, and that number is actually in kips. So the glass module made of 1 centimeter thin glass could take around 37 kips of load, 37,000 pounds. Again, this is equivalent to around like 17 tons of load. So clearly shows that this structure can be constructed out of the glass and it behaves really well. Now we're actually moving to the stage to basically figure out the construction detailing of this module, and hopefully we'll be able to assemble this for the next round of Glass Tech or another events related to glass technologies. To give you another insight about the typologies or the expansions of the typologies of the structural system to work with, I'm going to show you the work of one of my PhD students, Mustafa, who is basically expanding the palette of design for structural designers by coming up with some ideas in subdivision techniques in force distribution. So this is a cellular unit that I showed before. This is a spatial cellular flow of forces. And he has recently showed that with particular approach in controlling the force, you're able to translate a cellular system to a cellular system, which is quite efficient. And why this is important? Because the cellular systems mainly rely on buckling performance, and the construction of their nodes is actually quite challenging, that it's very difficult. But using this technique, you can translate this force flow into cellular system that is a 2-manifold system and relies not on buckling, but also on a shell behavior or double curvature behavior. And you're significantly improving the structural performance while providing many design options for architects. Yeah, he has also shown that you can generate periodic structural systems or forms that are applicable in the field of material science. But in terms of performance, for instance, the cellular systems are quite stronger than the cellular system, and the performance are almost 3 times better than the cell-based polyhedral system. So soon you would expect some compression-only cellular structural forms as a result of this manifestation. Now, to close this talk, I would like to basically get back to natural structures and give you a little bit of information about the history. So this is a cross-section of a trabecular bone, and you can clearly see that the material has been distributed more or less where the stresses are, right? We know this after a long time because there has been a lot of research in this field, and this is becoming actually, this has become quite obvious for us that nature knows how to distribute the material to make light-weighted structures. But an interesting fact about George Hermann von Meyer, who was basically a anatomist and physician at Zurich University, and he was a contemporary of Carl Kuhlmann, who was basically the first person who established the methods of graphic aesthetics. Interestingly enough, von Meyer was influenced by Carl Kuhlmann, and in fact, once he saw this drawing of the force flow in an internal cantilever beam on the left by Carl Kuhlmann, he started to relate the existing structure of a bone to the external forces and distribution of that. Later on, this became a famous law, which is called Wolff's law in the field of biomedical engineering, that the internal structure of a bone adapts itself to the external loading condition. And this is an interesting approach. In fact, nature has found its ways through million years of evolution to align the material where the stresses are, right? And this is super interesting. There are many biomimetic research is happening, especially in the field of architecture. But the important thing is that for what forces nature does this? And with this question in mind, we came back to the natural structures and tried to use the graphical analysis to understand the boundary condition or the forces that nature has designed for in order to understand the structure better in nature, rather than just replicating the structures by looking at their geometry. This would actually help us to understand what are the boundary conditions and what are the loads that nature tries to optimize itself for. And then we can learn from that and adapt that approach in architecture, structural engineering, etc. So this is the work of another of my PhD students, Hao Zheng, who is looking into the structure of a dragonfly wing. And he's extracting the force distribution using the graphical aesthetics from that basically pattern. And he's reconstructing the wings of dragonfly wing and dragonfly and basically compare it with the actual wing. The interesting thing is that the force distribution based on the reconstruction of the form force diagram quite matches very well the thickness of the members in the dragonfly wing. So this is amazing, because now we understand that the methods of graphic aesthetics also applies in nature. Now we can actually do a lot with that, right? So this is again an ongoing research, and unfortunately I can't share with you more. But again, this is very exciting, and I hope that I will be able to share this soon with you, the results of this work. Now that I come actually to the end of my presentation, I would like to close it with another ongoing basically work in our lab, which intends the educational extents of this method. So recently we are developing an interactive web-based tools for people who would like to basically explore this method and learn and understand and play and see the results of this. And this work has actually been funded by National Science Foundation. And soon I would be able to share this with you, and you can explore it online. All these possibilities of form, force, and basically the relationship between it. Thank you very much.
Great. Hopefully you hear all the applause from our 200 viewers right now, 200 plus viewers.
Thank you very much.
Thank you so much for that. And not only did we learn a lot about the content, I think we learned a lot how to present too, the professors and the students, the way you organized the story of this from the early history of how you got into this research. So thank you for that great presentation. We're going to start our kind of Q&A discussion part of this event. And before we started our little bit clumsy YouTube live, we were able to talk more casually. Professor Sungul Hong, who's online right now, he has some shared history with you, Masoud, as we discovered. And he's the one that actually had the idea of inviting you to lecture. So I wanted to invite Professor Hong. He's basically our resident expert on concrete at our school.
Excellent.
He really is doing a lot of interesting research with concrete. So Professor Hong, do you have any questions or comments?
Congratulations for your excellent seminar, and you give us some intuition of bio maybe imitation structure. So could you try to simulate your new structure by the 3D printing using some concrete?
Very funny. Yes, very funny to mention. Yes, we are actually starting a collaboration with an industrial partner here in the United States. unfortunately, I cannot disclose the name until everything goes well. So we'll be able, yes, but we are looking into 3D printing concrete with them. And because as you may know, the infrastructure of the US is quite old and dilapidated. So it's actually quite an important time for everyone who wants to contribute to the reconstruction of the infrastructure to revisit the idea of first of all, minimizing the amount of material and maximizing performance, because concrete, as you may know, has many negative environmental impacts. So less use of concrete is preferable. But again, the question would be that we need let's say, advanced techniques to be able to produce these complex structures yet efficient systems, right? Yes, it is something that we just started looking into.
Okay, once again, congratulations on your very nice research work. Okay, thank you.
Thank you very much.
I want to put Professor Hangman Zhou on the line here. He heads up our fabrication studio. He makes incredible large-scale fabrications every year with the students, and you see him and his students just slaving away and suffering, but then, which I'm sure you do as well, Masoud, when you make these things. But I just wanted to ask Professor Zhou, could you have any comments or questions? I think you're muted. Oh, there you go. Yes.
Yes. First of all, thank you for your excellent lecture. It's very inspiring, and but the work is very nice, and then to me it's like some sort of artwork. But, yeah, but
thank you.
when it kind of apply to the actual construction level, it should be scaled up, right?
Of course.
Yeah. So I have some question about, but your system so far is like working in a very closed system with a very pure force flow. Yeah, but when it comes to the actual, the buildings, it takes a lot of different types of the forces, such as lateral forces, wind load, and then live load, seismic load, or something like that. So do you have some idea how you kind of dealing with this kind of very pure system into a very dirty
resilience
situation?
Resilient system. So one thing is very interesting about the performance of these structures, and this is a very interesting question and very important question, as you mentioned, because the loading scenarios, it's very unpredictable in the actual work, right? It's very like a nature, right? So the interesting thing is that for instance, for Hydrocrete project, we compared the performance of that frame with the regular frame that had to be designed for the, if you visit our paper, I can actually refer to it, but it had to satisfy certain regulations by the code, right? Construction code. And still, we figured out that if we wanted to compare a regular frame structure with the structure that we have, the performance is 12 times better, right? So we had a factor of 12 times at least, but this is very case by case. You can't really say it for a particular system. But here are two directions you can go, right? One direction is that you basically increase your design load, right? To make sure that your dominant design load that you are building that structure is actually more than any other loading scenario that might actually happen in nature. So this is one thing. And you know that because your system is quite efficient for that dominant load, you are still saving a lot of material, right? This is for sure. So this is one approach. The other approach is that you basically look at the environment you're building. For instance, Eiffel Tower, right? The Eiffel Tower was designed based on using graphical aesthetics. And if you look at the geometry of Eiffel Tower, it was designed for wind loads, not gravitational loads, right? So understanding the boundary condition, the dominant loading case for your site basically helps you to use that dominant load in your design stage. Obviously, you're completely right. If your structure is not going to be as pure as it is, but if you understand the boundary condition better, you can assume that your dominant case or dominant design load would be the load that you are the most afraid of.
Oh, I understand. And then that you're saying your system, you said that the 12 times stronger than kind of normal
12
systems,
times
right?
more efficient than the regular
more
frame.
efficient. So that basically
but efficiency, okay, it depends again how we assess efficiency, right? Efficiency can be assessed based on the use of material, but 12 times is a factor of safety of 12. That's what I mean. Because if you if you visit the paper we were actually mentioning in there, that if you wanted to, so I did not mention anything about the density, the relative densities of these structures and the mass that you're using in that. But for instance, for the Hydrocrete project, the entire concrete usage was 3.1 cubic meter. 3.1 distributed in 50 cubic meter of space. Right? This makes the relative density 0.06, right? The spanning versus thing. And then you compare this, the spanning capability, with the regular frame and try to use the same material with the regular post and beam and try to span it. It would become impossible. Now you would say, okay, I'm going to increase my depth of beams for a regular system, right? To design, to span that. And if you compare it with the codes, we did this actually in our paper to provide a comparison. We get 12 times a factor of safety compared to the material that you're using. And this is only for that, only a structure. And you can basically do this case per case, right?
Okay, understand. Thanks for your explanation. And one more question that I have to ask you is that to me it's like to apply this system into a kind of building scale, not like a furniture scale, but like the bigger scale, like bridges or
or airport terminals.
yeah. I think to me it's like it's more efficient to use in the small scale or really large scale, not like building scale.
It's an important intuition what you're actually referring to. One of the limitations of the graphical methods is that it does not take into account the self-weight of the structure. Right? This is important. So the self-weight of the structure is not considered in this method, and none of the graphical methods are basically working with self. So self-weight is another additional component that you need to basically design for when you're dealing with the very large scale systems. But again, there, if you assume that you're depends on, again, what dominant force load that you're designing for, right? So for instance, in the stone buildings, right, the stone bridges or etc., there the self-weight of the structure is just so big that any other loading scenario does not matter, right? But definitely, if you want to reduce the self-weight, you have to face different types of performance. That's why, by the way, we are going for the 1 centimeter thin glass as a glass bridge to see if we are reducing the behavior, how we need to take into account any kind of asymmetric loading scenario. What would be the behavior? We still don't know. We're still exploring. But this is very exciting because if we can show that you can reduce the self-weight, but in the meantime, get the basically the performance that you were looking for, that is an exciting moment. That's exactly what we're looking for, and you were looking for too.
Yeah, understood. All right. One final question is that do you have a plan to kind of develop some scaffold system to kind of assemble or disassemble your structures? I saw that in your table movie, at the end of the table movie, you have some
yeah, those are so we had to, because exactly. But we again, that was minimized because in some members we had to do that. So yes, these are all great research direction. You know what I mean? So for instance, the entire concept of locking mechanism for the member, right? So that is, for instance, that can be developed for a larger scale system, so that if you put a member in place, the locking would take into account any bending moment as a result of the self-fade. So it would basically obviate the need to have any formwork. But that needs further exploration, obviously.
Okay.
And in my structural lab, unfortunately, we don't have the facilities to do these kind of works. But these are all exciting ideas that can be explored, because you can significantly reduce the amount of material, but the spatial assembly is a beast.
Okay, thank you. Thank you for your lecture and all the comments. Thank you.
Well, excellent. I want to introduce another one of our professors, Professor Chun Choi. Where Professor Hong is our resident expert on concrete, Professor Choi is our resident expert on love. He talks about, theorizes love and architecture in space, but also he's one of the curators of the next Seoul Biennale, which is a very huge exhibit we'll have in Seoul. Professor Choi, can you make any comments or questions?
Hi, good morning. Thank you for spending time with us instead of watching the town hall forum as everyone else. It's much more soothing to listen to you than either of those candidates. And yes, it would be lovely to have one of your structures as a pavilion as part of the
it would be an honor.
Biennale next year. Then your $10,000 construction cost was also very
well, that was wrong.
But then it seemed like it didn't include all the
doesn't include labor.
That doesn't include labor. Not at all.
Highly skilled researchers in your lab. But it did impress me a lot that this promise of intricate artistic form that was only available for the few and the powerful or the religious contexts are now going to be available for the masses by making it more digitized and more more robotized. And the way your students and your researchers were building them by hand also was more inspiring to watch, and how this could also become like a weekend a sort of hobby for a lot of these people. And we can provide these tools so it becomes easier to design as well as to fabricate. It will indeed become, I think, something that many more people can use much more easily and become accessible. So I'm more excited about that possibility than making it applied to infrastructure or airport, large-scale urban projects.
Absolutely.
So
part of the
you
reason
jumped
that
right into the furniture scale after doing this
because of the limitation. Because of the limitation, first of all, machinery, lab, etc., and also the costs. Right. If I wanted to make it bigger scale, first of all, I needed to have different construction techniques and budget also. Right. When I started my lab, I started almost with zero machinery, nothing, no equipment, and no support. Well, very limited support. I'm really grateful from Weitzman School of Design. But from construction point of view, we are still, we have a lot of limitation, and I hope that by the end of this year, you would be able to accomplish certain projects. So we would be able to produce these structures using advanced technologies like 3D printing or robotic fabrication, etc., etc. But what you saw here, it was all developed with zero access, I would say, to advanced digital tools that currently many people are using. And we had to deal with all those limitations. So you don't see it from outside. It looks like that. Yeah, this is great. They just produced this in a week. No, but even the 3D printing for the mold and the formwork for this took a long time because our 3D printer was very small. Again, we didn't have capability to expand it because of, again, the space limitations, budget limitations, etc., etc. So I'm really hopeful that by basically showing these examples and exciting and basically receiving more excitement, you would be able to attract some funding to invest on our infrastructure and lab equipment and machinery and basically look into the digitized way, as you said, to produce this in a more efficient manner, right? We have efficient structure, but the efficiency of construction is another thing.
Right, so not just the structural efficiency, but then
the construction efficiency.
Methods and, means and methods will be more efficient.
Exactly.
I have just one more question, a more boring question about your glass bulb structure that you made for glass tech. And I understood that you were using annealed glass and making them into a volumetric polyhedron and then stacking them like almost like tiles. But then why would you insist on using annealed glass and then usually?
No. That's annealed glass is just to show the potential of using a simple window glass to make a structure that can take 37 kips of load. But obviously for the actual structure, we're going to use laminated glass, a safety glass. So that's a real structure. For
yeah, because I was worried about
just for no. This just shows that again, part of the reason is the budget constraint. So we have this budget constraint. We just want to show that with very simple techniques, right? If the design methodology is right, you can achieve a lot. And if you work on that material, and if you basically optimize your construction process, obviously the entire 0 to 100 production costs and the efficiency in the lifetime, everything would be affected by this design, right? But as I said, we have to demonstrate the potentials, and always the demonstration comes by showing the working progress using very inexpensive materials.
I understood. I thought you were just setting up the challenge that was as tricky and
no, but the laminated glass eventually for the bridge is going to be around 1.5 centimeter, but it's going to be a safety glass. It's not going to be a window glass.
But the connection will still be just tape?
I can't reveal the connection now.
Okay. Oh, that was my next question. I'll have to wait.
Yeah. Soon.
Well, you have to bring the project to the Seoul Biennale then.
Oh, that would be cool because that would be awesome because we are actually designing it for assembly and reassembly. So yes, if it gets completed by that time,
we could also do a remote thing. So we fabricate and install here, and then you can collaborate over there.
Yes, exactly.
Do it. That will be more futuristic anyway.
I'm glad we can make this connection. Yes. Well, good. Well, we'll talk more offline about that. That's great. I want to introduce our another professor from our department, Thomas Kang. And Professor Kang is an expert in structural dynamics. He's also a fellow at the American Concrete Institute. And I remember also Professor Kang has written a lot of papers, not just on concrete, but on the repair of concrete. I think that becomes really important because buildings get older and we have to repair things. So very interested in what Professor Kang has to say.
Hello, Masoud. I'm Thomas. I was very impressed by your presentation, and I learned a lot of things, even in a short time. So thank you for that. I have several comments or questions. First, actually, in response to Professor Zhou's comment, generally gravity optimized structure like domes and shells, they are very good in resisting lateral loads too. Naturally, it's already having the capability to resist lateral loads. But for concrete thin members, it's sometimes vulnerable to unexpected low velocity impact. When you're moving this structure to a certain place, and when you assemble this or transporting, you may have some impact. So, and you don't want to see cracks, before even installed. So, to remedy that possibility of the cracking damage, maybe we can think of using like fiber reinforced concrete or polymer wrap concrete. Recently UHPC is getting more accepted.
That's exactly what we're using.
Yeah, because we're thinking of rear structures, and it's actually prefabricated, or maybe precast. So we got to think about that too. And in your compression test of the your model, it would have been better actually if you test the same concrete same
Yeah.
height, same volume, but
Yes.
just a cylinder.
Yeah.
So that, I mean, you
We have
compare
done that.
the
Yes. Yes.
elephant weights.
Yeah.
But I was wondering, as a structural engineer, that you know, in comparison with the concrete cylinder with the same volume, same height, what would be the capacity?
So, yeah, with the same volume, note that your cross section of concrete would actually be reduced.
Right.
You see what I mean? So it's not going to be the same because if you fill it with concrete, the volume is not going to be the same. So if you take the same volume and if you want to basically create, it would become a very basically thin column, right? So the steel, we have done this test, and very thin column, yes, you might say that it would be subjected to buckling, right? But it might actually take more loads or as equivalent load as the spatial structure that we designed. But note that there is a term that is really important that we should not forget, and that is the relative density or the quality of a spatial spanning, right? The spanning process, that is very important. So if you want to just talk about the vertical applied load, obviously a block of concrete can take 1,000 elephants, maybe, right? But if you're talking about the spanning and within that spanning, how you basically minimize the material or how you distribute the material in three-dimensional space, definitely this is a more efficient system.
Yeah, I agree. Yeah, I understand.
But
So
great comments. Yeah.
It's a great that actually you actually make hands-on mock-ups and also you provide web tools. I think a lot of architecture students need to use their tools. Of course, they're using their own software like Grasshopper to create a similar simulation. But it seems like using your web tool, they can do a much better job. So I like that to be introduced in our student group. And actually, many of the students are taking this. So I hope that it's helpful. So Professor Choi mentioned about the applications in a real scale, maybe in the campus as a pavilion. But I really want you to collaborate with the industry because you're concerned about the connection and some other concerns. So I wish that you actually finally build like monument like Sagrada Familia in Pennsylvania.
Well,
So
thank you very much.
that's my last comment.
Thank you. I really appreciate your comment. Thank you. The Sagrada Familia still is under construction, so I hope that I can build something that I can see it's finished.
The modern times, construction getting faster. So
yes. No, but I really appreciate your comment.
Well, excellent. We're going to switch over and get a couple questions from students now. So the professors don't hog all the airtime since we're running out of time a little bit. And one little preface story is that last year we visited your office, Masoud. I took about 12 of my students to visit, and we contacted you just very last minute. We barged into your office. We all crammed in there. In COVID era, we couldn't do that. And you were so generous to set up a small talk for us, even though I contacted you last minute. So I really appreciate your presence as an educator as well. Of course, your research is incredible, but as an educator, I think you're very generous. And so it's very inspiring. The flip side is that my students tried to, emulate some of the structures they saw. They didn't know what they were doing, so we totally made some very ugly things. But they ended up very exciting as well. But we didn't have the expertise. So I echo Professor Kang's comment about having these tools available in some primitive sense to help students. I think that'd be great. So anyway, thank you again as an educator. We have a question from Park Chi-sil.
Thank you for your motivating presentation. It's really nice to put a face to your name. Actually, we've studied your thesis in our lab seminar. And while reading it, we had some difficulties in understanding all the mathematics in your thesis. So I have two questions.
You want me to answer the mathematics question right now?
Not in mathematics. First one is is it okay to use your Rhino add-on, 3D graphic aesthetics, without full understanding of underlying your theories? And second one is, what would you recommend to us to study for better understanding of your theory?
Yeah, so good questions, very good questions. So the Rhino tool is a tool that you can use, definitely. But you need basic understandings related to the boundary condition, because obviously you can design a variety of different really exciting structural forms that are spatial. But note that those spatial structural forms are designed for all those boundary conditions that or the loads that are keeping that in equilibrium. And in reality, if you don't have those loads to keep it in equilibrium, obviously your system is not going to be efficient, right? So, so having said that, it is always good to basically start with very simple, for instance, compression-only shells, or understand where the location of basically the supports are, and basically go from there by basically increasing the complexity in each step. But in terms of where you can learn more, yes, I agree with you. There is not much material out there. There is a computational framework developed by Block Research Group as a tool, but it's a little bit of expansion of the 3D graphic aesthetics. We are developing this online web tool. Basically, it's soon is going to be available, so it's interactive. It starts with very simple examples and goes to more complex examples. Then you can actually step by step take these things and understand the entire behavior. But the other news is that I'm actually putting together a manuscript that starts everything from the beginning and explain this. And hopefully by the end of COVID, this would be ready and you would have it. Maybe it would be too late. You won't be at a school any longer, but you're always a student. You're always learning. So, and feel free to reach out to me or my students if you have any particular question related to your work or design.
Okay, thank you very much.
Sure.
Thank you very much.
Great, excellent. And we have a question now from Junho Lee.
Yes.
In the architecture department. Yes.
Yes, thank you for the lecture. It seems that there is the tendency that the whole system consisted with the uniform material, but the question is that couldn't the adaptation of the tension members, like divided the tension members, which is cost less, improves the efficiency of the system?
I'm not sure if I understood your question. You're saying that if we include more tensile members, it would increase the efficiency of the system because it depends on your design, right? So if you're designing a cable stayed bridge, if you can actually make that system out of cable because it's simpler than concrete, yes, you would do that. If you want to make a composite structure which has both compression and tension combined, then obviously you have some members that are taking compression and you have some members that are taking tension, right? But if you want to predominantly design based on tension, then you might actually need to reconsider your design objectives, right? I'm not saying that everything should be compression only and everything should be either tension only. There should be a combination of tension and compression. In fact, if you're interested, I would actually refer you to read our paper called Geometric Degrees of Freedom and Non-Conventional Structural Forms. So in that paper, we are showing that even the existing compression-only structures with the same force distribution can be turned into compression tension combined. That's exactly your comment, that basically reducing the number of compressive members to tensile elements for the same distribution of the force. I would definitely recommend you to visit that. But again, these are design options that you make as a designer, whether you would like to make a compression only, compression combined, or basically tension only system.
Thank you.
Sure.
Excellent. We have one last question from a student. Is Nami Lee online? Nami? Oh, yes. Oh, I'm sorry. Oh, okay.
Yes.
There's so many windows. I didn't see your window there. Okay. I'm sorry, you're not a student, but let's.
Okay. I was very impressed by your presentation, but still I'm hungry, for your specific knowledge to learn. Actually, I'd like to agree with you. The graphical approach is not dependent on the scale at all. That is totally independent of scale.
Yes.
So only depend on the ratio of dead load or live load and etc. So, but anyhow, to avoid the unexpected loading cases or some member deformation, we have to provide somehow alternative load path in terms of redundancy.
Exactly.
Would you do that?
Yes, in certain cases. For instance, if you want to design bridges that they definitely need to be designed for dynamic loadings, right? This is exactly, by the way, that the method that Robert Maillard did in designing his famous Salginotobel bridge, right? So you design the structure for self-weight or for the dominant load case, and then you basically take your asymmetric loading case and then move it along your structure, and then push, basically overlap all these load paths together to get the final structural form, or basically push overing these all the funicular pathways to create the material. Obviously, yes, that's another method to work with. We haven't done this in 3D graphic statics because dynamic load was not this. But if we want to move to dynamic loading like bridge design, yes, definitely we need to consider.
Yeah. By the way, I'd like to learn about the technique regarding the subdivision.
Yes.
Or do you have any specific way of subdivision to make the form?
Oh yeah, that's exactly the research that I showed that my PhD student is working on, that the subdivision is actually turning the cellular to cellular. This is one of the ways, but obviously, yes, it doesn't exist right now as a source that you can use, but this is part of the package that we would like to provide online also that you're working with, but it's still not available. But you would see that if you subdivide it, would give you multiple examples of what subdivision results in what form, and then you can clearly work and play around with that. But hopefully this would be ready by the end of this year.
Okay, almost the last question regarding the last slide. You are showing the dragonfly's wing.
Yes.
But
as a cantilever structure.
But it looks like to me 2D graphical approach.
It was a 2D graphic statics, yes.
Then the force also implying forces.
Yes, so I didn't get into that much detail about that. This was a 2D graphical analysis. It was not 3D. Okay. But if you go to 3D, the dragonfly wing is actually a 3-dimensional structure. It's not 2D. It looks like it's 2D, but it's not actually 3D. It's not 2D. But on 2D pattern, we just wanted to explore this and entertain the idea that whether in a 2D pattern this applies, and with a good percentage, you can see that the methods of graphic studies can predict the sizing of the members, and that was the most important lesson that we get from that.
And one last advice from you I'd like to have. This kind of graphical approach really requires a lot of patience, not only skills. So how do you encourage the students to do this one voluntarily?
The thing is that, well, first of all, it depends on what tool you're using, right? If it's if they have to do everything geometrically by hand and construct it, I understand it requires a lot of patience, right? But if you have computational tools, you can easily do that. The most important thing is that that's the approach that I have in my studio. If you tell them design the same structure without the force, try to do it. It's impossible. It's very difficult to come up with that design, or just like really precisely design it. You have to use many unknown black box tools, and eventually you don't know what to do with that. You don't know what happened that you ended up with that structure without having any control over it. But if they want to develop that control, they have to be patient.
Okay, thank you very much.
Great. And so we're out of time, so we have to close out this event soon. Professor Kim, sorry, I thought you were a student. I'm getting so many text messages, and it's a positive thing that we're getting text messages, Masoud, because it proves that there's a lot of interest in your research, and it also says that this is to be continued. our collaboration. This is the beginning of our collaboration. I hope there'll be many more to come. And so again, thank you everyone on Zoom, but also on YouTube Live for attending this. And it really was very inspiring for all of us. And I also want to invite the viewers that on October 30th, we have Kai-Uwe Bergman, who's a partner at BIG Architects, Big Architects. He's speaking at the same time, 9:30 a.m. and that's 8:30 p.m. Eastern time in the US. So please join us again for a similar event. And Masoud, I think you might know Kai-Uwe because he teaches at University of Pennsylvania every now and then. Maybe you cross paths.
Probably, definitely.
There's so many famous people that come to your school. But again, thank you again. And this was a wonderful beginning of a discussion.
Thank you very much. Thanks for the invite. It was a great pleasure. Thank you.
Great.
Great to meet you all.
Pleasure was ours. Thank you.
Thank you.